Hi everybody, my name is Paolo Gai, and in this short video I'm going to show you how to use the fast board interconnect and the transceiver of the Xilinx Zinq Ultrascale Plus to get more than 16 gigabit per second remote RDMA between FPGA. The outline of the presentation is the following. First, we will do a brief introduction of the AXIOM H2020 project. Then we will describe the cluster setup with the Zinq Ultrascale Plus, and we will do a live demo of the cluster setup, including a performance analysis. Let's do now a brief introduction of the AXIOM project. The AXIOM H2020 project was a research project funded by the European community, where various partners, you can see the logos in the slide, actually joined together to implement a cluster of small embedded boards. If I have to describe the AXIOM project in one slide, basically what we did is that we designed a small embedded board with trying to bridge the high-performance computing and the cyber-physical systems. We connect the boards together using the high-speed transceivers of the Xilinx Zinq Ultrascale Plus, and the target was to implement RDMA for the fast transfers between the boards. And then we developed a common programming paradigm, which is OmpSs clustered, where we use OpenMP on top of the GASNet library to implement a transparent FPGA acceleration and communication. And we use that for video and audio processing in the smart surveillance and speech recognition area. The AXIOM board is a small form factor board which is using the Zinq Ultrascale Plus ZU9EG. So it's a multi-core, it's a 4 cores with 1 gigabyte of DDR4s and with other important features such as a trace port for software tracing and also the power management measurements using shunt resistors. Important thing is the AXIOM link. There are 4 USB Type-C connectors on each AXIOM board, and they are used to connect the high-speed transceivers. So theoretically you have a 20 gigabit per connector bandwidth between boards. The AXIOM software stack is also completely open source, so you can find device driver, memory allocator, all the utilities that we are showing as open source in the AXIOM website. Let's now describe the cluster setup that we have done with Zinq Ultrascale Plus. The first thing is that we have to recognize that interconnecting FPGAs with a fast interconnection is not a trivial task, because it is not only involving the physical connection, but also various levels of software abstractions. And so what we implemented in the project was a multi-hop connection in the FPGA, including the topology discovering and routing in the cluster. We support for message passing RDMA, and also we do Ethernet TCP tunneling to allow running the normal TCP/IP application on top of the fast RDMA transfers. And also we support for efficient memory allocation on top of the Linux machines. The implementation provides 3 APIs at different level of complexity, and it has been tested on the Ultrascale Plus ZU9EG. The 3 levels of abstractions are the following. There is a high-level abstraction, which is the OpenMPSS pragmas. So OpenMP pragmas that you use to describe the parallel structure of the program. Then there is a mid-level, which is a GASNet communication system. And there is a lower level, which is the user libraries, which are directly connected to the device drivers and the network interface. At the high level, there is the OpenMPSS programming model that allows you to describe asynchronous parallelism and heterogeneity. Look at this code. With just 3 lines of code, you can parallelize a matrix multiply. Then there is the mid-level, which is the GASNet communication system, which implements active messages. An active message is a message which is not only transferring data, but requiring an action on the remote node. We have 3 kinds of messages, and those kind of messages are actually routed on top of the AXIOM link, which is using the transceiver of the FPGA. Finally, at the low level, we have the AXIOM User Library, which can be used to exchange data, so to send and receive raw messages, which are very short datagrams, long messages, which are RDMA transfer, where the destination address is decided by the remote node, and write and read memory of remote nodes, so remote DMA, which can be synchronous or asynchronous. There is also a memory allocator, which is able to allocate the memory in the RDMA zone of the AXIOM network interface. And also there are a set of utilities to manage the cluster, so set and get the routing table, get the status of interfaces, and so on. This is the cluster setup. You can see the boards which are connected to each other. Each board is equipped with 4 USB Type-C connectors, and there is only one USB-C cable is required to connect 2 boards, because inside the cable there are 2 bidirectional transceivers obtaining the 20 gigabit per second bandwidth. So the boards can be connected in a random way because the topology is automatically discovered using a discovery algorithm. The AXIOM cluster features on the top of the hardware interface provides you a set of features. The first thing is the user space network management. So you can have diagnostic, execution of remote applications. You have a discovery algorithm to discover the topology. You also have hot plug support. So you can at runtime connect the boards and remove the boards, and you just have to run again the discovery algorithm to reset the AXIOM link structure. Finally, there is the possibility to use the standard IP tools, so SSH, SFTP, and so on top of the AXIOM link, because everything is routed from a virtual Ethernet to the AXIOM link using TuneTap. We are now going to show the live cluster demo on a matrix multiply example. Okay, let's now power up the cluster. As you can see, we are now powering it up. As you can see, the LEDs are all on, meaning that all the boards are doing the boot process, and there is one serial line here which is connected to the PC. The PC is now booting, and the output of the boot process is on the console. We are now booting the system, and we are going to run AXIOM MakeMaster. AXIOM MakeMaster has the responsibility to load the AXIOM libraries and drivers and to run the discovery algorithm to discover the topology of the system. As you can see, the topology of the system is composed by a single node, which is node 1. We are now going to run the matrix multiplication example. This matrix multiplication example is running on 3 cores out of the 4 cores of the system. The matrix multiplication is going to run for around 10 seconds. Okay, we can now take advantage of the cluster configuration. We are going to now connect the connectors using the USB-C. The USB-C have the transceiver of the FPGA connected to them, so we are just connecting 2 random connectors out of the 4 available. We are now going to run the MakeMaster again, and in this case the discovery algorithm will run and will discover 2 boards, and the routing table will be distributed among the boards in the cluster. We are now going to run again the matrix multiplication. In this case, the matrix multiplication is going to use 2 boards, so 6 cores in total, and the total execution time will be a little bit less than 7 seconds. Okay, let's now add a 3rd board. The 3rd board, we could use a star topology, or we can do a different topology. In this case, we are going just to make them as a pipeline, so the 2nd board to the 3rd board. We are going now to run again the MakeMaster, and in this case the topology recognized will be a linear thing with 3 nodes, and node 1, 2, 3 are initialized. We are going to run again the matrix multiplication. In this case it will use 9 cores on the 3 boards, and the execution time is about 4.6 seconds. Okay, let's now add the 4th board. Let's do a strange configuration, so it's not a star topology but similar. We don't care really about the topology unless for the performance of the NIC, which has to do a multi-hop connection. We are now going to run again the MakeMaster, and you can see that it finds 4 boards. Okay, now we are going to run the matrix multiplication again, and in this case it is going to use 4 boards with 12 cores total, with a total execution time of 3.5 seconds compared to the 10 initial ones. We are now going to run again the matrix multiplication. In this time we are going to use getDeadline to constrain the communication thread which is running on the 4th core of each board. In this case, the 4th core will be also used as a computational thread. As a result, we get an optimization of the matrix multiplication. So we are going now to run the matrix multiplication using almost 16 cores, and we get 3.4 seconds, which is less than before. Now the performance measurements. As you can see, the actual throughput performance is around 16.8 gigabits per second for an RDMA asynchronous connection between boards. We also get an hyperf throughput EP over Axiom of around 3 gigabits per second on 6-8 threads, which is very high compared to the standard 1 gigabit per second Ethernet interface available on the board. We are now going to test the AXIOM cluster performance. The first thing we are going to do, remember we have the 4 boards connected in a cluster setup coming from the previous example. So we are now going to run AXIOM NetPerf on the second node. Please note that we are using SSH because the actual TCP/IP stack is actually routed over the AXIOM link over the transceivers. As a result, we are using this SSH. The NetPerf server is started on the remote node, and we are now doing some performance tests. The first test is a RDMA asynchronous of 100 megabytes of data between the 2 boards, and you can see that the performance that we got is roughly a little bit more than 16 gigabits per second. We are now going to launch a synchronous RDMA. The synchronous RDMA is different because we only send one RDMA transaction at a time, and the performance is a little bit less, so it's 15.7 gigabits per second. We are now going to run the same test using the long messages. Long messages are RDMA transactions where the destination address is not specified in the transaction, but is decided by the remote node. And as you can see, the performance here is 3.6, and it's mainly due to a memory copy between user space and kernel space. And finally, we are going to run the raw message demos. The raw messages are 256 bytes of datagram, which are just sent to each other, and the performance is very low, but it's comparable with the size of the messages, which is 0.1 gigabit per second. We're now going to test the IP over the AXIOM link, and in this case we are going to start the hyperf server on the node 2. Please note that the last number of the IP is the same number of the AXIOM network node that is given by the discovery algorithm at the beginning of the make master. So we are going to run the hyperf server, and we are running a standard hyperf test from node 1 to node 2 using multiple threads to get the best performance. And the best performance achieved in this case is in the order of 3 gigabits per second, and this number is thanks to the TuneTap implementation, which requires a few copies between user space and kernel space. If you have any questions or you're interested in running this kind of cluster setup, please contact us. Thank you, bye bye.